Okay, so welcome back. We have two exciting talks, one by Jason Lee and the other one by Kai-Shen Wang. And we start with Jason's talk, please.
Okay, so I'm going to talk about how transformers learn causal structure with gradient descent. It's by two of my students, Ishan and Alex. Alex is graduating, so if you have a position, look out for his application. Yeah, so, oops, this doesn't work, forgot. Okay, so today I'm going to mostly talk about in-context learning and induction heads. So this is copied from an Anthropic blog post. This is the post, Olsson et al. From about 2 years ago. Basically what they did is they trained transformers of various sizes and depths. And then they found that the loss has different plateaus for in-context learning. What you find is that the one-layer attention-only transformer, or just any one-layer transformer, will have difficulty doing in-context learning. The loss will never, it will just get stuck at that high value and it will never go down. And then the two-layer, three-layer, and so forth, all of these, the loss goes down to roughly the same value. So based on this, they kind of, they guessed or observed that in-context learning emerges at depth 2. And also they found at different observations that it roughly happens in the same time window across architectures. And then they decided, they kind of also showed that this corresponds to something called induction heads, which I'll explain. And the induction heads emerge roughly in this yellow window where the loss starts going down. So this is showing that in the same window, this induction head starts emerging, and I'll explain what this is plotting in a minute. Okay, so what are induction heads? Let's say I showed you this passage of Harry Potter, and I asked you to fill in the blank here, to fill in this token. And this is the prompt. So kind of the most natural algorithm and what an induction head does to solve this in-context learning problems is it goes back and scans for the occurrence of this token, DIRS, and then looks what comes after every DIRS. Then it finds that after this token, it's usually followed by LEY. And then it just copies over what comes after the previous token, and it fills that in. So this is sort of, they call this mechanism the induction head. And this is, they found that this is crucial to doing in-context learning. More abstractly, an induction head, if I give you a sequence and I ask you what comes next, you go back and look at who's the parent of this question mark, and then you go back and scan for previous occurrences of the A, and then you look what's after the previous occurrences of the A, and you return that to fill in the blank here. In this case, the previous A's were followed by B, so you predict B. Some other example of ICL taken from this Garg et al. Paper, also from 2 years ago, is essentially it's a meta-learning problem. Is you have a prompt that consists of n training samples, and then a test point, X test, Y test, and your goal is to predict what is Y test given this prompt. Do this because you don't know the dependent structure. You first have to learn that yn depends on the position previous to it. It depends on, for each of these, the dependent structure is that this one's parent is this one, yn minus one's parent is xn minus one, and so forth. And then what happens is the induction head, it copies down it slides diagonally the sequence. So, and it copies on the parent. So now under you in the residual stream, what you have is your parent's value. And it exactly corresponds to this, this DAG I've drew here. Okay, so these were the two examples of in context learning. The first one was sort of, it was pretending it's a Markov chain, the Harry Potter example. I just scan for its parent token and then look what's after it and then copy that over. And this one is, it learns that the y's all depend on the x's before them, and then the x's have no parents. And you can have more complex causal structures. And the question we kind of want to look at is, how do transformers learn this kind of causal structure given sequences that follow this data structure? Okay, so first we need a data generating mechanism that requires learning this causal structure. And the second, we're going to look at gradient descent dynamics on the pre-training loss. So the simplest case of this is to look at just Markov chains. What we're going to do is we just sample a transition kernel from a prior. The choice is not super important. Let's say every row is Dirichlet. The starting node comes from the stationary measure. And then we generate data, a sequence that respects the Markov structure. So meaning we sample Si plus 1 from the transition given Si. So sort of, if I gave you a sequence from this data generating mechanism, a very natural estimator, and probably what most of you would do, is just this simple counting estimator. It's also the maximum likelihood. You just look at the number of transitions from S to S prime and normalize it and return that as the empirical transition. If you had a more general causal structure, there's also a very natural estimator. For all of the optimization results in the talk, I'm only going to look at the case when you have a single parent, and the parent is before you, the sequence is ordered. And the way the data is generated is I have a transition pi from some prior. Again, the prior is not important. And I sample you conditional on the value of your parent. And if you're a root node, I sample you from some stationary distribution. And then the task is to predict the next token, or the last token in this case. The key is the actual data generating mechanism is not so important. The key here is that all of these sequences, they respect the DAG structure. Like if that was a DAG, and I generate data in this way, they would have different transitions and density functions because the pi is different, but they all respect the DAG, meaning like the conditional independencies are encoded in that DAG. You don't need connectors. So you can handle that ICL. The ICL you can handle, yes. Okay, so you can see this problem is not so easy to solve if I don't tell you the DAG. Here's a bunch of sequences I generated from a fixed DAG, all with different transitions. You can stare at this for a while. It's quite difficult to guess the causal structure. So basically, what you want to do to solve this, or at least one very sensible way to solve this, is you want to use the sequences to estimate the causal graph. And then after I know the causal graph, I can just use estimate the transition in context. Basically, given the graph, I just count the number of transitions from S to S prime in the graph and then normalize. And again, this is like essentially that maximum likelihood estimator. Just for a general DAG instead of just Markov chains. Okay, so the second step is quite easy to do. if you knew the DAG structure. So the main thing we need to study now is how do transformers recover the graph from the data set. So I'm going to take a brief detour into the language in which Anthropic uses to describe transformers. They had a series of blog posts that were quite influential, and they proposed to think about these as in terms of these residual streams. So these are the building blocks of a standard transformer architecture. First have the attention, and then the MLP. And then after every block, you add it back into the stream itself. That's these residual streams. And then you have a projection here or a mask to make the dimensions all correct. And then you read from the stream and then you go to the next layer. So basically the residual stream is where all the information of all the previous computations are. You could think of it as like a memory of what the transformer is using. They kind of proposed that the residual stream is very high dimensional, but you can divide into subspaces, and kind of you should think of these subspaces as somewhat nearly orthogonal. So when I write to different subspaces, I can later extract them still and get nearly perfect recovery. I forgot the term for this. I think it's superposition. This we weren't able to analyze. So instead, we're going to look at so basically, what I said would be very easy if the subspaces were exactly orthogonal. Like think of absolute positional embeddings. Then you can recover the exact position. But if the positional embedding was of dimension lower than the sequence length, like you can feel like from something like Johnson-Lin and Strauss, you can kind of recover the position, sort of. And that's kind of what they're trying to say here. Instead, I'm going to look at a different architecture that people use in mechanistic interpretability called the yes, I don't know how to go back. Yeah, so the residual stream is sort of it's basically every time you do some computation, you add it back in. It's sort of just like the residual connection, I guess. But the point is like, what Anthropic wants to say is that the dimension here is never growing, but you can still extract this information. And empirically, this is essentially true, although it's not very clear how to show this. So the alternative is we'll look at these transformers with just one hot tokens, which is kind of standard, and then one hot positional embeddings. And then we'll replace any linear projection, which is like usually you add into the residual stream. Now we're just going to grow the residual stream. This is literally what it means in terms of code, is that every time this thing is growing in dimension. So this is not a practical idea at all. Also, we remove MLPs. It turns out MLPs aren't needed for this task, and their experiments also were without MLPs. But with MLPs, they also found essentially the same thing. So this is called a disentangled transformer. It was proposed by my colleagues, Dan-Chi Chen's group, when they were studying mechanistic interpretability. But it's kind of just a very convenient way to mathematically think about these. They have the same exact expressive power. You lose nothing in terms of expressive power. But the embedding dimension doubles at every step. So you're growing, like if it were a deep transformer, you'll be in trouble. Luckily, you can't analyze dynamics of deep things. So when depth 2, this is not such a big deal. So we're going to look at these disentangled transformers where it's very nice because now I know like this is the result of a single computation of a previous step. And then and I know where to look for all the information. And it's very easy to interpret, which I'll show you using heat maps in a second. You don't have to think about this disentangling, sorry, this sort of superposition principle that Anthropic proposed. Okay, so this is now the heat maps of these disentangled transformers. So this is just the Markov chain. So this adjacency is 1 on the off diagonals, which is the chain graph. The first attention now in the disentangled transformer is there's token and position and token and position. The position attention block, if you stare at the output of gradient descent, it looks like the adjacency matrix. And the rest are basically zeros. And now on the second attention, remember the dimension's doubling every step. So there's 4 blocks now. And then one of these, this token block by that token block is an identity, and the rest are essentially zeros. And then there's a readout layer. It's just this one block here. Okay, so we also were not able to analyze training this entire thing. So let me tell you what we could analyze is we trained just this block and just this block. We do gradient descent on, we first changed the architecture to make it disentangled. So now, and then we just trained the 2 blocks that have interesting behavior. So this experiment is from running gradient descent on everything. And it's kind of as expected what Anthropic said is they also study the mechanism and it corresponds to these 2 blocks. And as expected, you get what they kind of figured out. And then we analyzed training these 2 blocks. But also when we did this, we found something beyond what Anthropic proposed is that when we changed the graph, they only looked at the case of Markov chains. We tried generating data from non-chain graphs, so other DAGs. Like this is that ICL example for the XY pairs. And we found essentially the same pattern is the first attention looks like this matrix, and the second one looks like the identity. So in general, when we tried this, we ran this experiment for many different DAGs, and we found that the first attention matrix, the position part of the first attention matrix is the adjacency matrix of the causal graph of the DAG. This is the same thing for a random DAG. Okay, so what is the mechanism in which the transformer is doing this? First of all, it goes back and it uses the first attention, which tells it the graph structure. Oh, sorry, question.
Yeah, sorry. So is your attention using softmax or?
Yes, it's using softmax.
Then how can it? But then the attention weights have to sum to 1, right? So it can't represent any adjacency matrix, or like if there's.
But these have single parent.
Right, but there are nodes in like the ICL one. There's like nodes that have no parent, right?
Then it's uniform attention.
Okay, so uniform represents.
Yeah. And then even if you have multiple parents, it's like just those are high and the rest are like 0.
I see. Okay.
It's just uniform on the parent set.
I see.
Yeah, uniform on the parent set. So basically you use your first attention and you go back and you look at who is my parent, and then you copy it down into the residual stream here. Like, in the normal transformer, you would add these 2. You would now have like half A plus half B. And then like they would be somewhat orthogonal-ish and you would have to extract. So we're just doing concatenation. So then now you have the B. And then the second attention, it's going to look at, compare the output of the first attention. It's going to say, which of these match this character here, this token here. So now I look at this, it matches, this one matches and this one matches. And then you go up on the residual stream, up 1. So then this A is followed by a B. This A was followed by a C, just going that way. And then now you know that your distribution should be half B plus half C, right? Because you look at where all the previous A's and you look at what follows them. This is the empirical distribution. Oops. It actually does this for all pairs simultaneously. Okay. So like I said, we're only going to look at training these two blocks. So two sub blocks of attention. Oops. Okay. I skipped a little too much ahead, but the loss function is cross entropy on the last token. You're predicting the last token. F theta is a transformer. Theta is the two attention matrices, A1 and A2. And then you're just minimizing this with gradient descent. So what the theorem says is that here, actually, so this one I say it doesn't cover your case of the pairs. But I think in the paper, there's one that does. So here I just stated the strongest mixing thing, where everything is, the transitions are all lower bounded. And then the loss converges is something going to 0, t to the power of c gamma. C is a very tiny constant, 1/50, I think. This is not so surprising. This is saying it can solve the problem. This one is telling you something more interesting. It tells you how it solves the problem. It says that the first attention actually does converge to the adjacency of the causal graph. So as a corollary, if you train on data generated from Markov chains, like what Anthropic did, you would learn this first attention would be 1 on the off diagonals, the adjacency of the chain graph. I should say something about OOD. This is a workshop on domain adaptation. There is an OOD result. You can have pi tilde not be from the prior. So it's something unseen in the prior. It needs to satisfy the same mixing conditions. Then with high probability here, you'll also be able to learn pi tilde, although you've never seen it before. And this is kind of very intuitive because let's say we're looking at chain graphs. Like once I know it's a chain graph, the maximum likelihood estimator always works, right? Like I don't need to do anything special for pi tilde. Like that estimator works for any Markov chain, regardless. And so this is almost obvious. That once you know, you learn like the counting estimator, it's immediate. That estimator generalizes out of distribution, as long as you respect the DAG, that you can have any transitions. Yeah.
Building on the point you just made, why does your theorem need the data to come from a fixed prior? Right? As you yourself just pointed out.
I think it's not very important. The prior is not very important.
So you think there's a version of this theorem where the data has the same causal structure, but maybe is generated adversarially, for example, instead of taking distribution, that might still work?
That probably wouldn't work. Like if you had data from the same Markov chain, it wouldn't work because it would just memorize the transitions of that one chain.
There needs to be enough diversity.
There needs, yeah, I don't know exactly what the right notion is, especially for the dynamics part. Yeah, but it's just, yeah, it's something about diversity to prevent it from doing the memorizing solution. Yeah.
So just following up,
yeah.
What was the condition on the generation sequences in the theorem? What was
the transitions need to mix. They're lower bounded.
Lower bounded.
They're lower bounded. Yeah.
The same lower bound, correct? The same gamma.
The one I stated here was just order of 1/s, where s is the number of states. In the paper, we have more complicated ones, basically saying that you can have disconnected components, but each within the component is lower bounded. And there's some to cover that case. The ICL case, yeah.
That's the transition matrix. That's what it's going
Right.
to be. So it could be a single transition matrix, always the same.
Oh, no. It comes from a Dirichlet prior. Sorry, let me go back. this p pi, it's Dirichlet basically. Think of it as Dirichlet. So you have some distribution on pi's, not quite Dirichlet, but something, Dirichlet conditional on this, let's say. Okay, so now let's look at what the gradients look like. It turns out the gradient of the first attention is very, very nice. It looks like something like the mutual information, the chi-squared mutual information between Si and Sj. It's not exactly this, but for the purposes of sketches, it's close enough. Why do we want it to be mutual information? Because the mutual information is maximized between you and your parent because it has because of data processing inequality. So just think of this as like per row, think of it as a vector. And then this vector has its maximum at the position of your parent. So like, for example, for a Markov chain, you'll eventually learn that you maximize between Si and Sj, and then I will just be j minus 1. So by the data processing quality, you're maximized sort of in the right place now. So you'll attend to the one immediately before it, or you'll continue, that entry has the largest gradient. And then it gets fed into softmax. So linear attention cannot do induction heads. And the reason is you do need the softmax because otherwise there's no way to like have something go to infinity basically. So basically the correct entry will grow at a faster rate than every other entry. Every other entry also grows, but then in the softmax, they get squished down, right? Like in softmax, only the fastest growing one. And then data processing ensures the fastest growing one is the parent. So that's what's going on in the first attention layer. And in general, this is always true that the mutual information is only decreasing. So you're always maximized at when J is the parent of I. So it's basically the gradient is a vector. The largest entry is in the correct place. It's true throughout all time t. And it gets fed into the softmax. And the softmax only keeps the largest one. So then this gives you the causal graph. This should remind you kind of like Chow-Lu. Chow-Lu is you compute all the mutual informations and you build a spanning tree. This is like easier because you know the ordering, right? So you don't need to do the spanning tree. I know I can only depend on ones before me, so I just look and keep the largest one. So it's essentially, you can think of it as just the greedy algorithm when I tell you the ordering of the graph. Yeah. I'll talk about the multiple parents in 1 minute.
Okay, thanks. Sorry.
Yeah. So yeah, actually right here. So the case of multiple parents is of course very important. N-grams are exactly this, like all of NLP before 2010 or something was 5 grams. Okay, so can we say this? Can we at least show that transformers can mimic n-gram models? The constructions are very easy. There's several constructions we know of. I think there's one that uses multiple heads, which I'll show you experiments on. There's also ones that use depth to do this, but we have no learning results in terms of dynamics. So this is basically, it depends on, this is a 3 gram. It depends on the one before it and 2 before it. And if you train a 2-layer attention only transformer, you'll find that the first head attends to the one 2 before it. The second head attends to one 1 before it. And you can show quite easily this computes the maximum likelihood. It just counts the ones based on the causal graph again. And there's also a similar thing using depth. Yeah.
So is the problem trying to reproduce that inequality that you have, the initial information for the gradient? Is that?
The problem is, I think, let me get that 1 second. Yeah. And so this is just the same thing. I think it's like a 4-gram. Okay, it's the same thing from some other thing. I think the reason why analyzing the gradient descent is difficult is that basically, if a head is a neuron, if you think of it as a neuron, each one, there's some symmetry in the beginning. You don't know which one goes to which one. I think it's essentially the same in a 2-layer network, is we don't know which goes to which. And even in 2-layer models, we only, in feed-forward MLPs, we only know how to handle this under like orthogonality and Gaussian data. Here, I don't know what orthogonality means. There's the data. Yeah, so I think it's essentially for the multi-head construction, you need to do the symmetry breaking in the beginning. If you have an n-gram, you need n-1 heads, and then I need to know which one goes to which. And for the depth construction, I think it's also a similar thing, is there's no reason for it to, like the depth construction is sort of each one, it shifts the sequence by 1. I didn't draw it here, and then you keep shifting it. So if you shift it n-1 times, you get your residual stream has all your parents. But like, I guess they need to be learned like somewhat simultaneously. But there are some interesting empirical results of, for example, this paper by Ben Edelman about sequential behavior. And it observes it learns the best unigram, then the best bigram, and then the best trigram for this 3-gram model. Unfortunately, the best bigram is not necessarily a subset of the parents. So yeah. So to learn this, I think you have to even learn how to undo it if you, yeah. Let me just finish. Yeah, so it's kind of nice to get lucky. The gradients look like some quantity we can recognize, the chi-square mutual information between positions. And then as a corollary, now you can show that you learn induction heads like Anthropic found. And there's some connections between this and like sort of algorithms we're familiar with in graphical models. Yeah, and I really like the disentangled transformer, although it's not used, I think it's only used by the interpretability people and theorists, but I think it does help you see like what parts of the model should learn what, and then it is a lot simpler. Even with this simplification, there's still many things are hard. Yeah, and so this is still not quite realistic. It's only looking at positional dependencies. You can imagine there's no context being taken into account here. Yeah. And then also, like I said, what we have now only works for the single parent case. I think it should be true, but for general DAGs, but we don't have proof of it. Yeah, and yeah, beyond just absolute positional embeddings. Thank you.
Questions? Thanks a lot.
I'm curious. Okay, so going back to Xiaolu, I'm curious if there's a setting in which you think it can actually learn. So Xiaolu, it does something a bit different because it's greedy in a very different way. Like it's not locally greedy; it's more like globally greedy. So I'm curious if you think that transformers are able to do that. I was trying to think like if for example you saw a bunch of variables and then wanted to predict the next thing dependent on some a joint distribution which follows some tree. So I want to set a setting where you need to learn a tree after seeing everything, right? So you don't get this ordering. This ordering makes it very easy, right?
The ordering makes it easy.
Right. Do you think that the gradient dynamics can mimic this global greedy that's necessary to actually find a maximum spanning tree and actually execute Xiaolu?
So it would have to be not an autoregressive, right? They're thinking like
you can phrase it also regressive. Imagine you have two classes. You're essentially doing a binary classification task where the last token is just asking, you get all the sequence, and then I'm trying to compare whether I'm in one of two distributions, with both of the distributions follow the same tree, but with different distributions, right? So that would force you to. Okay, maybe we can. I mean, I think you can create a situation where even without a regressive, you need it, and or you can just think of it in a bidirectional transformer. The dynamics would probably be the same.
Yeah. I was probably not, but I don't have any real.
Thank you so much for your awesome presentation. For the multiple parents case, like if it depends like mostly on one parent, but a little bit on the second parent, can you tell that by the magnitude of the mutual information between each of them, or no?
Do you mean like reading it off from this?
Yeah.
I don't think we ever looked at that.
Okay, sorry. Thank you so much.
So I was wondering actually how these bounds that you derived, how they depend on the number of states on the capital S. So you had some convergence of the gradient descent, but
the
then
numerators all, I forgot if I wrote it. Oh, sorry, all of the numerators, I didn't write it. All of the numerators here have poly S. Everything, every time you saw this in a theorem, there should have been a poly S. Like same with here. One of these, okay, this one for sure has a poly. Yeah, actually this one too. All of them have poly. Yeah.
Okay. But you can't say anything about the degree or so. That,
I don't remember. It's yeah.
Another thing, can you maybe elaborate a bit why chi-square comes up and not Kullback-Leibler? So because you train with log entropy, so it's closely related to Kullback-Leibler. But why do you get something close to chi-square in the end? I mean, they are somehow similar in certain regimes. But,
I don't. Yeah, I was initially a little surprised too, but
do the softmax plus the all pairs.
I don't think I have a good. Yeah, I don't think I have a good intuitive reason. Beyond that, if you just wrote down the gradient, it would look. It looks like. It looks more. It looks like this essentially. The gradient looks like that. Yeah, I don't know. I have no intuition.
Someone wants to pose a final question? Okay, then. Thanks again, Jason. Yeah.